And there's 7 types of additive manufacturing. If you're familiar with the ISO ASTM 52900, I'm going to go through them. I'm going to talk about my research, but I'm going to start by just kind of giving the landscape of additive manufacturing. But more specifically, what we do at UTEP is we've got about a 2 decades history of interrupting these processes and injecting electronics and then continuing. So the idea is we want to make circuit boards that can compete head-to-head electromagnetically, but that bring sort of the complex geometries and customization that you get from additive. And I'll describe that in a little bit more. But we have all 7 forms there. This is actually Oak Ridge right here. This is the MDF. It's possibly the best equipped additive manufacturing lab in the world. And this right here is actually, this part was aluminum with a huge robotic welding system. And so that's just a cool example. So it's kind of funny, I'm talking about El Paso. I realize I put a picture in for Oak Ridge, but we'll talk about that. It's like, you know. And so what I'm doing research in, I think, if you look at additive manufacturing, the 2 industries that stand to benefit the most are really aerospace, where you have, you know, the ability to do a lattice and get just enough strength at the lowest possible weight, but also to get complex aerodynamic structures. And then the second industry would be biomedical, where I could actually scan my arm and I could get an implant that was specific to my human anatomy. And so I'm more on the aerospace side. That's just where the funding has come from. And in what we would go after, what we're trying to pursue, electromagnetics, I think, is an area of opportunity, just because you can get these, you're going to see a lot of different complex geometries and how they can provide lenses and antennas. And the other thing is thermal management, you know, that you can put microfluidic channels, have high surface areas. And so that's a big area. So electromagnetics, smart tooling, which is a little bit away from the electronics, but I'm going to show a little bit of that. Sand casting, where we definitely have electronics. I do a lot of computer vision. I probably won't talk about that today because it's sort of outside the scope of this conference. Smart metal would be the last thing I do, and then 3D printed electronics. And I know this conference is more about flexible electronics, and there's some examples. They're actually printing the shoes, Adidas and New Balance shoes with an elastomer that's very durable. I've got at least one example where I'm working with the National Football League in the United States to like insert sensors and things of that nature. And just a shameless plug, I've always got to do this. I happen to be the co-founding editor of this journal, Additive Manufacturing by Elsevier. It currently is the #1 impact factor for all manufacturing. And that started in 2014. I basically ran it for the first 6 years, and now we get like 3,000 papers. So we have a horde of associate editors that take different topics. And then I moved over to start a new journal where that's 5,000 words and up. This is 5,000 words and less. We're trying to get this like 2 to 4 week turnaround with a single cycle review, where you're either provisionally accepted or rejected, and within a month. And so that's been, I think, something that the researchers that I've talked to have really been stressing, is they have an idea and they feel like they're getting scooped. And many of the sort of traditional additive manufacturing journals, there's probably 15, excuse me, are just overwhelmed with submissions. There's just a finite number of reviewers. So I would definitely encourage any of you, if you're doing something that's got complex geometries and electronics, either one of these journals would be, we would definitely want to publish it. And then, yeah, I guess that's all I got to say about that. Oh, well, there's one more thing. So a couple of years ago, I was a keynote speaker in a South African conference, and they wanted to know a little bit more about the journal. And so I asked Elsevier for some data, and they gave me this. And I don't see electronics in this at all, but we certainly get a lot of electronics papers. Maybe 50 out of the 3,000 in a year. But basically what you've got is metal is really a big area. And this is the processes that do that. We're talking about microstructure, metallurgy, things like that. I'm an electrical engineer, so I don't fully understand that. And then maybe over here is more of the polymer work, where the electronics generally would go, but I'm going to show some cases of injecting electronics into ceramics, into metals by the end of this presentation. And then certainly a huge area is simulation, trying to simulate these processes and so forth. Sorry, I got a little bit of a cough. I'm also wearing the same clothes I had since Friday because I flew here and my bags got lost. And I'm jet lagged and I haven't slept maybe 6 hours in the last 2 days, but I think I'm always at my best under those conditions. So here's the idea that I'm going after. Additive manufacturing gives you complex geometries where you can have spatially varying lattices, you can get ceramics, polymers, and there's a lot of work in that area. But if you could integrate that with other more traditional processes like robotic placement, ablation, ink deposition, and so forth, then you can kind of come up with this sort of wacky montage of different items. This was a piece of a satellite. This is an antenna. I've already shown these different electronics. That's a magnetometer, microcontroller. We don't print the microprocessor. We print what we can and we place what we can't print, basically, it's the idea. And then, well, this is Oak Ridge. This is not electronics. This is titanium. It's a lattice and it's a hand, but it has pneumatic tubes to allow for its actuation. And I'll show a little bit more about this later. That's a microcontroller, an accelerometer. And this is possibly the dumbest thing we've done, to be honest with you. But everybody kind of sees it in operation or in action, and they immediately understand what we're doing. The idea is you can roll the dice. The accelerometer can be read, in real time. You know that it's moving. When it comes to rest, you know which way down is because of gravity. And then they blink the lights on the top. And a kindergartner, a senator, the Secretary of the Air Force, whoever has money in the government in the United States sees this and goes, oh, I get it. I understand what you're doing. But it's not a good example because when we go to casinos, we were trying to sell this as an idea, see if we could get a little spin-off company. And they're like, hey, you can spatially vary the density. Kind of like what we're doing here, right? Where it's thicker, the struts are thicker here than here. You have full control. It's a digital process. And we're like, of course we can, no problem. And they're just like, kill it. We don't want anything to do with you and your cheap dice. And so it's a dumb idea. You really want to do traditional manufacturing for something like that because it needs to be so regular and dependable and believable. But the cool thing is you could have put your name. You could make 10 of these and each one could have, the high roller of the casino's name, and it could be customized. So the big benefit, of course, is complex geometries and customization. And then the idea that you can put in with a bunch of other processes, things that make it, intelligent, programmable, and so forth. And I'll give you some examples as we go forward. So just let me give you the landscape of traditional additive manufacturing. Since this conference really isn't about additive, I figure I could give you that as a starting point. And that dice, for instance, was used with this technology. And this is the first form of additive manufacturing. It was developed in California by Chuck Hall, but it was, they say, simultaneously developed in France and in Japan with Sony and a university in France. But Chuck Hall basically commercialized it. He created a company called 3D Systems, which I think is either the first or second biggest additive manufacturing company in the world. But the idea is you have a vat of liquid photocurable polymer, and a laser, as you saw, basically selectively cures one layer at a time. And this build platform descended as that happened, and at the end it pulls back out. This happens to be like the spinal cord of a young girl in El Paso back in like 2005. And we did this as like a pre-surgical model for a doctor. So that's what the center at UTEP started to do, was biomedical and trying to support, the local physicians. The problem with this technology, or at least used to be the problem, is that this is because it's photocurable, it's not the best materials in the world. It's relegated to photochemistry. And in El Paso, where we have a sun that just beams down on you, that UV light means that you get continued curing for years, right? And things tend to become brittle, they discolor, and so forth. But that's changed, and I'll show that as we go forward. Okay, so this is a company out of San Jose, California. It's the same technology, but now you're getting an image coming up from the bottom that you don't see. And they figured out a way to make the bottom layer not solidified. So there's like an inhibition of the curing. And this is maybe 8 times faster than reality. But the materials that so it's just like the cool younger brother of stereolithography or vat photopolymerization. But in this case, the materials are really fantastic. It was a company that is in San Jose, but it's based out of Virginia Tech, out of their polymer science group. And I'll show you some interesting things where they're doing shoes. The Adidas 3D printed shoes is printed with this system. I also work with Form Labs, which is doing the New Balance shoe. And well, I'll talk about that in a moment. Then a system we had developed, stand over here, at UTEP, and this was maybe 2009, used an image and focused optics to do much better resolution. Now the X and Y resolution in this case would be like 5 microns. The Z direction depends on the depth of penetration into that photocurable resin. But back a long time ago, we were doing pretty small items. I don't know if I can see the scale here, but I think this is probably like 100 microns. And then what's interesting here is we actually did multi-material. We would swap out materials layer by layer. So if you notice, this peen is clear and the helix is red. And we're about to hopefully do some really interesting things with 3D printed batteries, which I'll talk about in a moment. But there's several companies now that have gone in this direction. And again, it's using the same technology that's in that projector. Instead of a laser point-wise curing the resin, you're hitting it with an image. So theoretically, it should be faster. And I think the resolution's a little bit better. Okay, the very best in terms of resolution, however, is 2 photon vat photopolymerization. And instead of shooting an image or a laser at the surface of the liquid, this actually focuses the energy sufficiently to get a 2 photon reaction anywhere in a volumetric volume of the liquid. And you're getting down to like 100 nanometer resolution. And again, this is the best technology available today. The leading company, I think it's in Carlsruhe, it's pretty close to here, it's Nanoscribe. Yeah, well, I guess you would know, wouldn't you? And although there's now a competing French company that's come out, and I just won an award, a grant to get the Nanoscribe system at UTEP. But you can just see it's pretty fantastic. And I think this image was from this is an old company. It's been around since the 90s. And there's a lot of interesting stuff of optics, biomedical needles, drug delivery, things like that. So this is I think really interesting. It's still, confined to photochemistry, which has its limits. But again, I think there's been strides in the materials that they're using now. And then the most popular, just in general, system is material extrusion. And this happens to be like a $500,000 system. Stratasys, the other company involved in 3D printing that's big. The patents expired for this in 2007, and that's where the whole desktop printers came from. That basically, if you get a $1,000 printer that's squirting out thermoplastic, it's based on this company and their patents. And furthermore, they had a patent for putting this in basically an oven to reduce the residual stresses, and that patent's about to expire as well. So the desktop systems tend to be out in the open, and that really limits the thermoplastics you can use, PLA, ABS, whereas this system can use Ultem, PEEK, much higher performing engineering grade thermoplastics. But again, that advantage is about to go away because that patent's about to expire. This was done in Minnesota, this technology, in like 1987. Okay, so you could actually do metals in both of those last systems if you do a thermal post process to get rid of the plastic and have metal particles or ceramic particles. But the processes that we're going to look at now have been right from the beginning targeting metals, which is really, you know, from the standpoint of structural objects that can, you know, bear a load. That's what mechanical engineers tend to want. And so if you look at this sort of, okay, so here we've got accuracy and surface roughness. And then you have a lot of traditional type things like polishing, lapping, grinding, die casting. The world here is this, the blue line is metal AM. And I'm going to talk about each of these, but there's binder jetting, which is an MIT technology. And depending on the size of the powder, basically ink jets down a binder into metal powder, and then you sinter it later. Powder bed fusion, this is probably the most widely adopted industrial technology. So they're making, General Electric is making parts that go into jet engines. They're doing parts that are well, they aren't not doing tungsten with that technology. They're using titanium, Inconel, high temperature, you know, really high performance materials and pretty good resolution. We're going to look at electron beam, the same category. The company that made this did jewel pretty. I'm not even sure what that is now. It never really took off. But then you've got directed energy deposition. I'll describe that. And that can be either wire or powder. And I'll show you both of those. And actually, with this one, I've actually injected electronics into it, which is kind of interesting. So this is a bed of powder of metal, and that's an electron being electromagnetically steered, basically to melt the powder. And then we're going to scrape another layer of metal on top of that, and a bed will descend, and layer by layer we'll build this metal object. And here you can actually see we're making like cubes or something. And here is, and this is electron beam. It's an Arcam, which is a Swedish company, and UTEP was the second university in the United States to have this technology. The idea of powder bed fusion, where you have a bed and some sort of directed, you know, laser focused energy coming down, was originally invented in Austin, Texas. And in about 2 weeks, the professors that did that are going to have their conference, which is a solid freeform fabrication symposium. And that's the oldest conference in additive manufacturing. And it's a pretty good one, by the way. If you're interested in additive, I would argue that a lot of the seminal papers in electronics came from that conference. Very academic, very international. The only problem is Austin in July and August, it's just terrible. It's so hot, so hot. So this is the same idea. You're about to see a recoder come across, putting another layer of metal powder down. And this laser's melting it. This, from an industrial standpoint, is the most widely adopted technology. And this is going into, you know, important aerospace, you know, components, jet engines, and so forth. Good resolution. They can use a finer powder in this technology versus electron beam melting. And so you get better surface finish, better accuracy. And there's been at least one case where there's been like a passive component in electronics put into this technology. The third, fourth technology that was invented was binder jetting. So this is this is like gypsum powder. And what's happening is you're ink jetting down 3 colors, a binder of 3 colors. To get full color control in 3 dimensions. You can see this is a virus before Corona. And this is a company called Z Corp. They've now been swallowed up by some other company. And I think if you were to take this, any one of those virus, and throw it on the ground and just shatter, it's not really functional, but it's great for modeling, prototyping, which is what this technology did originally in the 80s. You know, our idea now is the push is to make it, we're making end use products. But binder jetting it has come a long way. Now with further processes, thermal post processes, you can get full density. You can infiltrate the porosity that's left with a lower temperature metal that will infiltrate in. And I'm going to show you where we're printing sand, not as a final product, but to make a mold that we can pour metal into. And that's actually a big area of my research right now. This is actually an S-Max printer. My last university in Ohio had this printer. There's 2 in the US. But basically the idea is you pull it in sand, you mix it with acid, which happens to be a 2-part of a pure-end binder. So we're mixing that in. You're going to take it down, and this is the essence of binder jetting right here. This is the powder bed. We're going to basically come in and put one layer, about 250 microns of sand down, and then come through an inkjet selectively what we want to make a mold. So you'll see in a moment, I've got a couple videos of this later. If you were to take this mold and drop it, it would just shatter. But if you put molten metal into it, it can handle that really high temperature. And then, 4 hours later, the metal solidifies and the mold is sacrificial, so you just remove it. But this box comes out and there's your mold. Now, one of the things I'm doing here is you can put electronics into this to get new sensed data that's unprecedented, right? Sandcasting is from like 3,000 years ago. You get a box, another box of sand, you have a pattern, you punch into it, put the boxes together, put a hole, pour metal. I'll show some examples later. And that's been for, thousands of years, people have been doing that. The beauty here is you can get geometries you couldn't get before. You can get lattices, things of that nature. I'll tell you one thing I'm trying to do for the new students that graduate with a PhD from UTEP in engineering. I'm trying to make, I've got a Bhutanese bell design and I've got a UTEP logo. It's all digital, but then I can make every single one of them different with their name of the student in the program. So like something for a little extra cachet, for the degree. It's that digital customization and the complex geometry. It's very cool. And I think BMW is not using X1, but voxel jet. And some really high performance cars are getting some of their parts sandcasted using this technology to get, geometries that you couldn't get otherwise. But they only make 30,000 of those cars. The problem with this technology and additive manufacturing in general is the production rate, right? This bottle I can make in 1 second with an injection molding tool. But if I were to 3D print it, it would take 4 hours, right? Or maybe less, but it would take a lot longer. So unless there's an application need for that, a complex geometry or some sort of customization, it doesn't make sense to use it in general. So this is an Israeli company. My last university had this. This is called material jetting, where now you inkjet down the actual material you want to use. Originally, a company called Objet had a photocurable resin similar to stereolithography or bath photopolymerization, and they would just, the inkjetting would selectively deposit the material, and then it would just come by with a lamp, cure it, whole scale. Now they're doing ceramics, and I thought I brought one. This is actually, a previous video was showing the last university I was at in Ohio, near this Fraunhofer-inspired institute that I worked at. But you get really good resolution. Inkjetting gets you like 20 micron type resolution. And they're doing metals and ceramics. And of course, ceramics is relatively new because of the very, very high temperature of melting. Ceramics are hard to 3D print. But there's a lot of interest in that because of their thermal stability, chemical stability. And I'll show you later that it also has an electromagnetic advantage. It has a very, very good dielectric properties. Probably the least popular technology is sheet lamination. You put down a sheet of plastic here, that's what they're doing, and then you come through and eat away at that little layer, cut away what you don't want. So there's a lot of waste. One of the big advantages of 3D printing is that you really only put material where you need it. But this one doesn't do that. It puts it down everywhere and then it takes it away. This is an Italian company, Solido, and I think they may have unfortunately gone out of business because this technology is just not that popular. But I think that this could actually be an interesting case for electronics. If you look at like LTCC technology, which is tapes of alumina, ceramic in the green state, that you punch out holes and then screen print in silver pastes and then press and heat. So it's low temperature co-fired ceramics. You can make very high performance electronic substrates. Now in this case, it could be capped on, which could be a pretty good low loss material. But nobody's ever really explored that, but you could actually have a robotic placement where you cut away sections and put in components and then keep going. I've heard people talk about it. I've never seen a paper on it. In general, yeah, that system unfortunately has gone out of business for that company. This is, and I don't have a video of it. This is actually a 3D printed paper where they inkjet down just 2D color, both sides of the paper with an ink that soaks all the way through the paper. They stack the paper, glue them together, and cut away each layer. And so this is only for modeling, but the color and the resolution of this is pretty fantastic. It's an Irish company called MCore, and my last university had this one, but it's only for modeling and prototyping. And although I don't really have a good example of this in Ohio, there's a company called Fabriconic. It's not going to play. Where it'll take tape of aluminum or any metal for that matter, and it will roll it out and put a sonotroid on top of it, which ultrasonically vibrates it and applies pressure, and it gives a metallurgical bond with the previous layer. And then again, you have to go in and machine it away. You're going to see that in a moment. So the sheet lamination approach has sort of a waste associated with it. But what I think is really cool about this material for electronics is it's the lowest temperature process. You know, I showed you electron beam melting, selective laser melting, where you put a lot of energy in to melt powder. And so if you have electronics, they're not going to be able to survive. There's been at least one case where they put fiber optics into this structure, and then they lay metal out on top of it. And because of the very selective nature of the heating, the fiber optics survived. So that's something in 2007, I worked with Utah State University, which had one of these systems. We actually put electronics inside with, a deposition system and placement of chips, and not having thousands of degrees C of some high performance metal melting. It opens up a lot of possibilities. But I just don't see any of the sheet lamination approaches really being broadly adopted. Okay, and then the final one, now what's happening here is the metal powder's coming out of this side and the laser's coming from this side and coincidentally melting it onto the structure. So this is directed energy deposition. This is the first one. This came out of Sandia National Labs, about 3 hours north of El Paso, another one of the labs that was in the Manhattan Project. And this is definitely becoming popular. It doesn't have the resolution that you get from powder bed fusion, but generally speaking, the deposition rates are much higher. So you can build bigger parts faster. And actually the powder version of it's not that great for production rate when you compare it to this system, which is in an evacuated chamber with a wire and an electron beam melting the metal. And this is, from a production rate standpoint, this is by far the fastest metal 3D printing process. And then finally, an alternative to this, or a slight modification of this, is what we call hybrid. So this is DED. This is a laser, a laser and a powder. You see there's both of them going coincidentally, and you can see that it's adding metal. But what DMG Mori is doing is they bring in another head, and they can actually do traditional subtractive machining to get good surface finish and intricate detail. And you can see how it's, milling out holes, and it comes in and puts in another feature. And I've actually worked with the University of Bremen in Germany to insert electronics into this technology. And at Oak Ridge, we used a similar system, not this one, but very similar. And we just embedded a ceramic 3D printed object. It was nothing special, it was just a chunk of ceramic we had printed. But the idea is if we can make that ceramic large enough, and if we can embed electronics in the ceramic, then we can embed the ceramic into the metal. And I'll show you an example of that. So we're working on that. So those are the 7 forms of 3D printing. Now let me show you the wackier side of the world of additive manufacturing and talk about some of the stuff we're doing. And I've got to first complain that there's really no CAD support for what I'm talking about. This merge of mechanical and electrical engineering, where I need to put a circuit into a solid model, right? Fusion 360 and the German PCB company Eagle have come together and are trying to do this, but there's really no commercial efforts. What we've done in the past is we've used some sort of cadence or synopsis software to do a circuit, a PCB, and then we did SolidWorks to make some sort of solid model, and then somehow we basically deform them to combine them. And you'll see the different things we have. So you would put a little cavity for a chip to put in. You have little trenches that you can put conductive inks into. And when you do that, you can make a circuit that's, curved. And that's just, there's no commercial software to help. The way I do it is I just get a bunch of masters and PhD students to do a lot of manual activity, and unfortunately. But so far, everything we've done has been simple enough that you can do it. But if you were to do something really sophisticated like a cell phone, that would take thousands of traces, that would be different. And so this is certainly an impediment to the progress in electronics and 3D printing. The second thing, when we look at plastic substrates, is that since about 2004, we've been putting conductive inks down. And frankly, the world of 2D printing, you guys know more than I do. I think it's been inhibited by the fact that we can't cure these metal inks at 850 C or 1000 C if we're putting them on Kapton or paper or wherever we're printing. And so the conductivity suffers. So we came up with at least one solution at UTEP where we would print a thermoplastic object, and then similar to sheet lamination, we would ultrasonically submerge a wire into the structure. And we could do that, and I'll show some examples of that. And so, of course, then you can compete head-to-head with the printed circuit board in terms of bulk conductivity of copper. That, think about a PCB is plating. Typically, a 1 ounce plating process would give you about 37 microns of thickness, and you get 100% conductivity. If you look at some examples of different geometries, different inks, you're really penalized by inks. And I'll say that since then, that was one solution. The second thing we're looking at, this certainly isn't flexible, but you can 3D print ceramics now, and you could put inks onto those, and then you can fire those at much higher temperatures because the substrate will not limit what you can do. So I'll show that in a little bit. So here's like a process. This is thermally. It's actually got, you can see some electrodes. So we're through ohmic heating. We're heating up the wire, putting some pressure. This is ultrasonic. You see the wire going into this little hole, and it's being vibrated. To locally heat it, and it just sinks into the plastic. This is actually a singly curved surface. That's an antenna. It doesn't look like it's submerged, but it is. And this is actually a really big 3D printer called BAM. And Lockheed Martin at a conference used our technology to embed wires in that. And in this case, what they wanted to do is they wanted to power. This is a huge part of a satellite. This was metal 3D printing of a fuel tank. They just wanted to power some circuit up here. But what's interesting about 3D printing, or what's bad about 3D printing, is you can see the layers going up. And of course, that means you have anisotropic strength, that in X and Y, it's stronger than in the Z direction. You can delaminate. And so one of the serendipitous benefits of this wire embedding is it acts as a reinforcement agent. And it basically can hold it together and improve the strength of the thermoplastic object. That's not what they were interested in. They wanted power and ground in electrical connectivity. So here you see a polycarbonate substrate, some sort of white plastic. And here are the wires that you can see we've ultrasonically submerged into the substrate. And what's interesting is that there's an inherent porosity in this technology, which meant that when we push this in, instead of bulging out, it actually remains flat and gives us a planar surface upon which we can continue to print. So you can have wires that are pretty close together. You know, if you think about a printed circuit board and the traces that typically are used, it can be like 50 microns pitch. And here we've got like a 36 gauge wire, 120 microns, and we're getting them, you know, progressively closer and closer together. There's some problems with this, and we got a lot of funding to work on it. I left UTEP for 4 years, and so this has been sort of dormant. But the idea of being able to put dielectrics and conductors that are high performance together in arbitrary complex geometries, there's a lot of potential applications that benefit from that. We tried to actually then put chips in there, and then we would laser weld them. That's kind of come to a dead end because we were welding the wires, but we were destroying the components because of the heat. So laser welding didn't really do what we needed. And ultimately, you have to connect these wires to components. And if you're doing microelectronics, that's a difficult thing to do. You have to have some sort of ink or conductive epoxy or something like that. If you're just trying to do a wiring harness or something along those lines, it works pretty well. And so we were always trying to miniaturize these 3D printed objects and make something, you know, that was small, but in reality, we realized this might be better for bigger objects like CubeSats that might be 30 centimeters by 10 by 10 that need a wiring harness that can handle an amp of current, where maybe a printed ink wouldn't be sufficiently conductive. So back in 2009, we published this in 13. One of my students basically started printing in a Stratasys system and manually putting in components. He just put a bearing in, and he's got one object on the outside and one object being printed on the inside that are independent mechanically. And the idea is he's trying to print a motor. And he also made it in such a way that there was no support material required, which would have connected the two objects. So they're completely independent. These are electromagnets. This is the Keck Center at UTEP. And he's going in and putting those wires in manually into little trenches. You're going to see this in a moment, right here. Well, that's what that process that I just showed you replaced. So we started manually, but we knew we were going to automate these things as we move forward. And he's about to put another bearing in. So now that object in the middle can rotate. And he caps it off. The whole thing took about 5 hours. That was a time lapse. Pops it off, that's support material. Propeller is just for dramatic effect. And then in this case, what I wanted to do was press print and have a robot walk out or fly out. But in those days, it was a heated envelope. You couldn't put a battery in there because they can only go to 60C. So you had to plug it in, but it worked. And this is a terrible motor because it's just a standard motor. It's not that big. It spins pretty quickly, but you could do a reaction sphere. You have a motor that's a ball. You just rotate in any arbitrary direction, and that's important for satellites with attitude control. But the bottom line is that you couldn't put in energy storage into that. I can tell you that young man was like a genius. He was from Durango, Mexico. Durango, that's what it's in Mexico. But I got 5 daughters. My oldest daughter, I was trying to hook them up. I just love this kid. And I'll tell you that that's just with that. The father coming in and saying, hey, you know, you need to meet him. It's like, they didn't go anywhere. Anyway, just a side note. So batteries, because of that project, that led to 2 things. I'm going to show a video in a moment where we did a lot of automation. But I actually co-hosted a conference in Chile that was supported by the Office of Naval Research Global of the US. And we were just going to do 3D printing in Santiago. But they have big lithium reserves in Chile, and this office down in Chile of the US government and the embassy wanted batteries, 3D printed batteries. There's not much work in this area, but there's a school in France that wants doing some work. So I met this young man, and he was headed to Harvard to be a postdoc. I talked him into coming to El Paso. His wife, who happens to be Mexican, who got her PhD in France also and was working for Renault, she came too, and they're just an incredible dynamic duo. They just recently got a $2.5 million grant to do 3D printed batteries, extracting the chemistry from Martian regolith, from Martian soil. But right now, our fingers are crossed. We have a $16 million Department of Energy proposal that should be funded by August 1st. So they got to tell us pretty quickly. But if we get that, it's going to change my career probably. I'm going to be doing batteries from here on out. But the idea is you can do an anode and a cathode and an electrolyte separator. If you can do multi-material printing, you can get these really complex interdigitated, architectures that would give you better power performance. This is very blue sky research. What we've been using so far is that photopolymerization. And now we're getting that 2-photon system to get the best resolution. And those aren't inherently good at multi-material printing. I did show a spiral in red and a pillar in clear. But the idea is that we would dissolve in precursor salts and then print 3 materials and then do a thermal post process that would burn out the plastic and cause a chemical synthesis to the chemistry that we needed in multi-material. So this is, high impact, high risk kind of research, but in any case, all coming from the fact that we wanted to be able to print a robot and have it walk out, and you need an energy source for that. And then that motor also led to a couple $1 million of funding to basically automate what you saw being done by hand. This robot really is overkill. It's just a conveyance system, but you saw 2 Stratasys systems here. You can see the inside of that system. It's material extrusion. It's putting out a thermoplastic. But the real magic of this was that there's another gantry system to the side that does traditional manufacturing, like machining, robotic placement. And here you can see we're machining, making it flatter, better surface finish, intricate detail. And we had heard that NASA was going to have an X Prize for somebody that could print a satellite, a CubeSat, which is 10 by 10 by 10 centimeters in 24 hours. So we were rushing to be prepared for that contest that never happened. But the idea, and here you see copper tape being put down and then being machined. That would be a ground plane for an antenna that would happen subsequently. You can see here we're placing a board that I designed into a cavity, and then you can just print right over the top of that to encase it in. Actually, I think I've already shown that, but the idea that you would also include this wire embedding. One of the problems we're having here is everything you're seeing is either PLA or polycarbonate. Polycarbonate is a great plastic, but the plastics we really want, and there's 3 that are space qualified and biomedically qualified, or PEEK, and Altem, and PEC. And all of those materials have to be in a heated chamber, because if you take them out in the room temperature, they tend to have residual stresses and warp and delaminate. So we've sort of been relegated to non-engineering materials in this case. And that project has kind of been put on hold. And then the idea here is this is the Sun Bowl. This is like a couple 100 yards from Mexico. The Sun Bowl is where like the Big Ten plays football on December 31st. And it's where our football team plays. It's like 50,000 people. Anyway, we printed a UAV, and the point was it had so much current going to that motor, you couldn't have done that with like a printed ink. It would be too resistant. And I want to say that there was a woman that was running over there. She called the police on my students. We weren't supposed to be there. I wasn't there. I had to like call the police department and say, "No, those are good kids. Don't worry, they're all right." And then just a couple other things. Aerosol jetting, which I'm sure most of you are familiar with, is actually invented in Albuquerque, just north of us at Sandia, and then it's led by now a company called Optical. They invented directed energy deposition, that metal process, and then did aerosol jetting for printed electronics. And of course, this gives you really great resolution. I did a 3D printed pill once. That's a microcontroller. It's a known die form. There's no packaging. So I want to print the package. And the package in this case was an ingestible computer. Turns out this was that photopolymerization, some sort of material that's like toxic. If you took this pill, you'd die. But the point would be, maybe we could fix that later. But just, I ended up getting a grant with the CEO of that company. And you can see here, that's kind of annoying actually, but here's the silicon. That's like 10 million transistors. In the 90s, that's what I did. I was a designer, logic and circuit designer. I went to become a professor in 2003. I couldn't get funding in it because it was just too industrial. So I started doing wackier things like 3D printed electronics and started to get funding. But just something that's interesting. You could actually put silicon in, and then the thing you're 3D printing would actually be the package of the electronics, which would be also something that would serve the application. This was just some other kind of wacky stuff we did in Ohio. That's or a prosthetic that has Bluetooth electronics embedded. And then we had a phone app that would just sort of track that. You could imagine there's a lot of biomedical, gating and walking type of studies that would be interesting. Pressure sensors. Here, this is a board. It's kind of like an Arduino, but I can get a little 5 by 5 millimeter chip from Texas Instruments that doesn't need a clock. It doesn't need anything except for power and ground. And then a couple of wires to do a capacitive sensing. And in that case, we use that to be as a proxy for pressure. You're going to see that I take advantage of this chip because it's just really convenient that I don't need a lot of extra external components. This is that dice that you saw. Again, the stupidest thing we've ever done, but here I think we even have a video. I've got the dice, but it's 12 years old and the battery died. We're trying to resurrect that project right now. I'll show you some examples of that. But this bad idea has led to millions of dollars of funding for us because funding agents understand what it can do, what this means. And it's just not a very good application, but it's like marketing, I'm like a used car salesman, So I'm trying to do another generation of this, and I want to do ceramics. And to do ceramics, I could print 2 parts and put a battery into them. When you print a ceramic, there's always a thermal post process. You have to put it at 1450 C for like 60 hours, cook out the plastic that was in the 3D printing. And when you do that, it shrinks. And obviously electronics aren't going to survive. But if you think about a tiered approach where you have this 1450 C sintering to get the ceramic to be full density or close to full density, then you put in conductive inks into these traces and you fire those maybe at 850 C, so you get close to bulk conductivity. And then put in the electronics that can only go to say 200 C for 5 minutes or 150 for a long period. And then you have a third cycle to basically adhere the electronics to superficial edges. That's kind of an interesting idea, but you're limited to only surfaces that are external, obviously. But if you could do some assembly, in this case, there's 2 parts. We're doing a study to use these little pogo pins to basically make electrical connections between the 2 sections. Then you could have parts that are inside, and that are on superficial edges that get mated together and are protected. And so right from the beginning, when we did 3D printed electronics, the idea was I'm just going to press print, and you're done, right? No assembly required. Now we're backtracking. We're coming back and saying, well, maybe some assembly, right? Because if you want to use ceramics, you just can't, those processes aren't compatible with electronics. So you put the electronics in and you figure out a way to connect 2 sections. And then there's some internal surfaces that can be, populated with electronics. Just something that we did maybe in 2007, a helmet insert. And what happens, what I'll show later, is that we actually work with the National Football League, not the football of everybody else, but the football in the United States, where we have a big problem with concussions. There's a lot of high-speed collisions. And the NFL they're actually playing games the last 2 years with 3D printed helmets because you can get these complex geometries that can help with the impact energy management. And I'll show a little bit about that. And another thing, just capacitive sensors in general, you know, you could touch this and it would light up. There was a circuit in there. We did a lot of studies and published in IEEE sensors where you could have fluidic channels. You could tell that there's water in the channel, salt water, you know, different things, because you're measuring the permittivity basically by doing capacitive sensing. And the idea that 3D printing gives you that sort of freedom of doing fluidic channels inside of a three-dimensional volumetric structure. Okay, so I showed you this. This is VAT photopolymerization. It's a company out of San Jose. Here's a shoe that you can buy right now, $300, but yeah, it's kind of expensive, or I'd be wearing them now probably. And what's interesting is the beauty of 3D printing is I could scan your feet, not just your feet, but each one individually. I could print a shoe that's specific to your anatomy. They're not doing that yet. The rest of the shoe is made traditionally. But what they are doing is using complex geometries to basically tune the coefficient of restitution so that when you put energy into the sole, it returns it. You could run faster possibly, and it's more comfortable. And what's really cool about this is I just told you the VAT photopolymerization has really bad material properties. It's relegated to photochemistry. Well, they've got it where they're making a shoe that you would step on 100,000 times through the life of the shoe. And these are very durable materials. So there's been advancements in the last 10 years where elastomer, soft, rubber-like materials can be printed into a very complex geometry and survive a pretty hostile environment. And so, of course, I'm like, well, how do we put electronics into this? And so the idea of this sort of assembly approach, and this is just sort of one idea, but it kind of is enough to give you a sense. You can make a sphere, it's 4 parts, and you print each of them separately. That process uses light to set the shape, and then afterwards you put it into a post-thermal cure with UV, and you get, you imbue the mechanical performance that I just showed you. Well, what about taking those 3D printed green parts, putting in components and wires, and the way you design the structure where it mates together, you could have internal surfaces that do anything, right? They could be curved, they could be diagonal. So you could have those superficial surfaces that populate with electronics. You have to do assembly, then you put it into the furnace and it becomes a consolidated single part with internal components. And here, that's a tensile bar at the end of it. We put wires into it. You can see that when you do that, there's actually 2 pieces that are been overmolded together. So this is a concept that we're looking at for ceramics, but also for elastomers. And here, okay, oh, is it going to play? Whoa. Oh, this is tragic. This is such a great video. This is Formlabs material. You can't get this commercially, but they're using it in the New Balance shoe. And so I talked to Formlabs in Boston, and they designed this, or I designed the lattice, and they printed it for me. And what you see is that there's 2 wires going into different layers of this lattice. And I put my fist on it, and basically there's a computer in the back that shows a graph, and you see the deformation. And then I punch it, and you see a spike. And so I got to the final rounds with our NFL in the United States to look at the next generation propellants. And I didn't get funding for it, which sort of surprised me. So this is a killer idea. But it turns out, and this is just between us, but the NFL, they don't really want to measure impact, right? They just want to stop concussions. Measuring this is potentially a source of like litigation, and there's a lot going on right now. There's even movies about concussions in the NFL. So unfortunately, I got to the final round, but I never got money from the NFL. And I think just would have been good branding to have that. I mean, the NFL is, I guess, a big deal in the United States. And then for the PhD students out there, peer review publication is like the essence of the scientific method. But I put that video, which unfortunately you didn't see, on LinkedIn. You could go to LinkedIn and look for my account. You can see that I hit it. But that video got it's at like 200,000 views now, I think. I had 100,000 views within a couple of weeks. And I could have faked that video, you know, so this is just trash in general, but the fact that I could get an idea out into the open space, and you see the companies, like, it's like Apple, Airbus, Boeing, I don't know why these guys were involved, or Apple for that matter, Intel, Microsoft, HP, you know, Paris, you know, Bangalore, LA, Detroit, you know, that you can really expose an idea to a lot of people. And I guess we were just discussing how maybe some people are more afraid to expose ideas because they don't want to get scooped. So I publish papers like mad because I don't want to get scooped. And you could argue some of this stuff could be patented and I could go after a company. I guess you have to kind of figure out which way you want to go in life. But I sort of embrace this idea of open source and just coming up with ideas, trying them out, and try to, you know, publish them so that other people see them, and then they do something different that's better. You know, humanity progresses. But I think the world of PhD students now is kind of changing. There's a whole new social media approach to disseminating ideas. I think you still have to go and stick a paper in a journal like mine and go through the brutal process of peer review, which is really pretty ugly. You know, I've had my feelings hurt more than once, but that, you know, that's where you get the credible ideas out, but at least to get early exposure to ideas that social media is changing the way we do science. This is just, okay, this is a video, those are the two wires, and it's a high-speed video just showing how those wires get closer together, and that changes the capacitance between them, and that's what I'm measuring. And then, well, we also did like two different materials. This is like an Alta maker. This is the carbon system, and it's spatially varying. You can't see it, but we're just trying to mess with the way the time that the energy absorbs, the de-acceleration of that structure. And it's just complex geometries that allow you to potentially protect somebody's head, their feet, their knees. A lot of biomedical applications for this. I got 15 minutes, I better hurry up. This is peak, and this, oh, the video didn't show another one. Oh, it's because I'm on that computer. Anyway, this is a very high performance thermoplastic that's space grade and biomedical compatible. And it has a span here. The problem is there's no support material for this that you need to put in here to allow for that overhang. And this company in Poland basically provided that for us. So in this case, it's the same piece. It's hit here, and then it's hit here faster, and it just crushes. The idea was we wanted the outer shell of the helmet to be made out of this material. Then a friend of mine in South Africa did a CT scan, and this is compliance to CAD. So green is good, red and blue are bad. I kind of like this video just because it makes me want to eat Skittles, but you can see that in the case where we didn't have the material, we had a lot of problems. In the case that we did have it, we had nice compliance to CAD. Nothing to do with electronics necessarily, but I just, yeah, it's just pleasurable to watch that. And then probably a technology that's the closest to being at a production rate is something called they call it MJF. It's really powder bed fusion. They inkjet down like carbon black and water selectively, and then they come in with a lamp and just melt the plastic. And so it can work really quickly. Where the black is, it absorbs heat, energy, and it melts. Where the water is, it stays cooler. It's like a detailing agent. And I did a study. I'm trying to figure out how to get electronics into this. Actually, HP, when they first came out with this, they actually had an electronics application where they were trying to, I don't know how they did it, but they had conductive and dielectric materials together. And I think it was because they inkjetted something down that would cause it to be conductive. And of course, it wouldn't be that conductive, but that was clearly one of the things that they were interested in. And so the idea, a lot of particularly German cars or car companies are looking at this as like plastic parts that can give you really complex geometries for a manifold under the hood. So we wrote a paper. So anytime you see green, it's the paper we wrote. What we did was we made these vessels, and we at 25 and 90 degrees C, we pressurized them repeatedly to 100,000 times to see about pressure fatigue. you know, and then we also did a study on, you know, submerging this into oil for a month and to see that the underhood conditions were a problem. We never saw a failure. The two failures you see here were when my graduate student actually put the heating rod and touched it, and it just immediately exploded. But 100,000, we did, you know, a whole statistical sample of it, and that was a project we did with ETH Zurich. And then, well, this I'm about to run out of time. This is just some electronics. This is some electronics. You know, one thing I was going to show, and I didn't know if I just didn't think it was appropriate. I'm going to the University of Nottingham this week to give a presentation. And about 5 years ago, the London Museum of Science did an exhibit that Nottingham sort of led about 3D printing. And Nottingham came to us and said, hey, we want your satellite piece. And we gave it to them. And it was in London. I don't know, it may still be there. I think it might be in Manchester Museum of Industry also. But right next to it, I got to go to the museum, was this gun that this University of Texas student had printed. And it was blown apart. You know, they showed the barrel exploded. And then the events of this week with the Japanese ex-prime minister, Abe, having been shot and killed, they say it's 3D printed. I don't really think it was very much 3D printing. But the idea of this sort of juxtaposition of like the good and bad of 3D printing, you can do, you know, someday you might be able to print me a new liver, which is probably an inevitability that I'm going to need, or a satellite component, right? Or the more nefarious things like guns, right? And I know Europeans look at the United States and say, oh, you guys are gun fanatics. And then inside of the United States, 49 states look at my state and say, you guys are just out of control, right? Texas. And actually, that's where the gun was printed. But now in Japan, you can get a gun by printing it at home. It's kind of terrifying. I mean, technology just explodes exponentially. And hopefully it will be used for the betterment of mankind, but it's not necessarily always the case. Anyway, so this piece was, it flew in low Earth orbit, and with 35 other university science experiments and CubeSats. We were a part of a CubeSat, and that's the CubeSat over there that had a power supply from a company. 6 of the satellites had that same power supply. It didn't work. So it's probably more appropriate to say that this is like, you know, the first 3D printed debris in space or something. It didn't actually do anything, but it had a microcontroller. We work with Sandia National Labs. It's kind of a cool project. I've got a project with JAXA. We're going to put another satellite. We're doing a ceramic piece. We're going to have a printed thermocouple and like a radiator, basically having a really complex surface because of the thermodynamics of being in a vacuum, trying to release heat. We're going to try and measure that. Here's the satellite we did. This is a 3-use. This is 30 by 10 by 10. And the idea is that there's a harness inside of it. It's not like real intricate microelectronics, but it's like power electronics. And you have the power, you know, over here you have solar cells. This is a University of New Mexico 6 CubeSat. It gives you a sense of how messy they are. And if you can, you know, integrate the wires into the plastic, then you could, you know, make it potentially better. And then the idea is that the wires actually strengthen the plastic, and you can do space grade plastics. So this has been sort of a focus area that we've been involved in. This is propulsion. Back in the day, you couldn't really put in like fuel, rocket fuel or anything like that into a 3D printer because they were heated. Not so much now, but there was a company called Busick that has this sort of coaxial copper surrounding Teflon. You put 5,000 volts on this thing, it will ablate. And that's in a bell jar in a vacuum. It's 3D printed. And it's got this little rocket in it, this propulsion. It's not going to send you to Mars, but it could certainly be used to make a university satellite, you know, face Earth and take a picture or something like that. So that was kind of a cool project. We never got funding for that, but I did get a publication. And then we've also done things like put tungsten powder into plastic. So you could print a satellite where maybe it's heavier on one side, but it shields radiation. And we went to a radiation source at Sandia National Labs and proved that we could actually attenuate radiation. In this case, it was X-ray. So I mean, you can get this in like your dentist's office, but there's more exotic types of radiation that people worried about because it causes the electronics to fail, get soft errors and so forth. Wow. Okay, so anyway, electromagnetic performance, plastics that are 3D printed are pretty terrible, but the ceramics aren't. And you have really high permittivity, so you can do things at the speed of light. You just, oh man, I'm really out of it. I'm gonna have to kind of skip through some of this. I'm gonna say like maybe 5 words. We've done a phased array antenna with the University of Arizona. We did this sort of pathological geometry, and we tried a whole bunch of different metals processes to see which ones work. And we went to NASA to show that it worked. This right here is a binder jetted version of it. And what you see is that they shipped it to my house. I didn't have the technology. They had to print it for me. My daughter ran over it in like a little Mini Cooper. And you can see it's definitely deformed and broken in one place, but it's a testament to the strengths of its material. This is like a ship in the bottle fractal antenna, a radiator and a ground plane structure. And then something we did with that aluminum antennas, we worked with the company Trumpf in Germany. It has a green laser that allows for copper, so you get much higher connectivity. Ceramics, you can just do some really cool geometries with this. But let me get to what is probably more important. So LTCC is an existing technology. It has tooling, so it's not digital, it's not like additive. But if we could compete with this technology, there's some real interesting applications. Well, we tried, I didn't get funding for this, but this is a ceramic printer in the International Space Station. The idea that ceramic particles float inside of that photocurable polymer. In microgravity, you get better uniformity of particle distribution. That's pretty ugly. This is an antenna. This is aerosol jetted dipole antenna on a zirconia. This is Draper Labs. They did this with plastic, and it inspired me to try to recreate it with additive. And that's what I came up with. But this is, you just see this incredible resolution. And the idea here is that's just a lattice, but you could spatially vary the lattice. Zirconia has a permittivity of 30, but if you have a wavelength that's 10 times bigger than the unit cell, it doesn't really see the unit cells. It just sees sort of an average. And so the permittivity here is higher than it is here because there's more air. So in a 3-dimensional space, I can control the speed of electromagnetic radiation. And by doing that, you can do things like a Lindbergh lens where you can bend light to a point with a lens. So a lot of interesting electromagnetic applications. This is the University of Arizona that came up with this idea. They did it in plastic. And then we're doing it now in zirconia. Nope, cool geometry, nope. They crack a lot, and we did some things to stop that. I'll keep going. Okay, 5 minutes. This is sand. This is actually my new love. This is that printer I showed you, where you're making sacrificial molds that you can pour metal into. And you can make geometries you couldn't make before. This technology has been around for 3,000 years, but now you can do things you couldn't do before. So that's 3D printed sand, and that hole in the top is called a screw. And you can then melt metal and pour it in. And then a day later, you crack open the sand. I'll show that real quick. So that's 3D printed enabled sand casting. Now what I do is stuff electronics into things. So of course what I did was take a little Bluetooth sensor. This is like a Dialog IoT. It's got Bosch sensors. This is 3D printed sand. We capped it. There's 2 of those sensors in there. That's a core that suspends down into a bigger mold. And that cavity that it's suspended into fills with molten metal. And you have about 2.5 centimeters of sand protecting it from the harsh conditions of the metal. In 2 minutes, that is reduced to like black powder. There's nothing left. But for 2 minutes, you get Bluetooth data out. It's, unprecedented. Recording of pressure, temperature, magnetic field, volatile organic compounds deep inside of this casting, right? So here, this is a part for a helicopter. That's magnesium. It's very dangerous. I shouldn't have been there. But that's my cell phone right there, and it's reading the sensor inside. I didn't know. They use this as like a weapon, but it's a very good aerospace material. It's very light metal. But I'm going to swing around, putting my face right into this. But you see, I'm collecting all this data. And for about 2 minutes, we just get this great data, you know, and this is really, it's turning the casting industry on its head. I get a lot of attention for that kind of stuff. Here's some of the data we collected, but you can see it's 2 minutes. This is the bottom of the mold, and we want to see how fast the metal runs. We can detect that. Here's a simulation, my friend Guha Managaran at Penn State. The color here is the speed, and you want it to be less than half a meter per second, or you get turbulence and porosity. And so here, what he did, which I thought was cool, is 3D printing. You can do like really cool designs to throttle the speed. And here you see the porosity difference, the improvement in quality. And then I got one more thing that I got to show you. Okay, no. Oh, well, okay, this is cool too. That's the sand printer. Instead of, we stopped it in the middle of the process, evacuated a cavity, put sensors in, and then kept printing. And the idea is we just want to see how these molds cure. But there's a pretty big catastrophe there, which is sort of entertaining to watch. So that's just a Grove Raspberry Pi Arduino sensor. And yeah, it's probably worth it just to see this. It's going to come in and put new sand on and inkjet down again, so no problems. Comes in, new sand right now. And you're going to see the inkjetter coming in and putting the binder in to glue this together. The first layer is fine. Does it again. And you're going to see one of these things springs up, you know, just because of the wire. And then when you're going to see it right there, you see it coming out, and this guy's just going to pop it and just drag it out. I just thought that was fun to watch. I'm publishing a paper on this right now. And that's a famous guy, Jerry. This is in Iowa. Anyway, that's what we printed. You see these sensors are fully embedded. For 28 days, we just monitor the volatile organic compounds and things like that. And one thing was that was in Iowa, which is just like the worst weather. And the snowstorm hit right after I got there and did that. And you can see that the humidity goes up and the volatile organic compounds go down. It's not curing. That's just, I just thought this was cool. This is a project I'm doing at school in Poland. Spatially varying lattices. I put that on LinkedIn, and metallurgists all over the world told me I was an idiot, because you see how it's brittle and things are springing off. If we didn't heat treat it, I'm an electrical engineer. I don't even know what heat treating means. I don't even know what that means or what it does, but the metallurgists were pretty upset. And then finally, last project, University of Bremen. This is a hybrid DED system. So it's going to blow metal powder with a laser and make an object. We sent these little inserts to Bremen, and they screen printed on a ceramic sensor that will handle high temperatures. And so we embedded it into metal bars just to show that you could actually put at least passive components into a metal process. That's the design of the sensor that they did for us. And this video will show you it in operation. And that's it. Gosh, I'm like 2 minutes late. So here is tensile bars that we're going to use. The inserts put into a cavity that was machined out, 2 wires coming out, a multimeter reading the sensor. And we're going to come in, and we're not going to actually put metal. That's a stitch weld. It's just a laser melting it together. But you're going to see we put a couple layers of metal on top of it. And watch the multimeter. You see the number changing. So you see the spatters, the powder. We're actually adding metal. And you can see that you can read the sensor while we're building it. That looks ugly, but we can machine that off, and we get this. And at the end, you get tensile bars, and that's what mechanical engineers use to find out how strong this material is. And so you can see that we actually measured it while we built it, at least the second half. And then after the fact, we had a sensor inside of metal, sort of a ship in the bottle concept. And people immediately criticized me because it was dumb. It's just a tensile bar, which is so boring. But then you compromise the structural integrity by putting that sensor inside. But of course, it's 3D printing, so you can compensate and make it stronger so that it's strong enough. But now you've got like structural health diagnostics, prognosis capability. And then let me just tell you this. This is Bhutan. And this is the architecture that we're copying. This is looking at my university going to the north. That's the United States. That's into the Rocky Mountains. All of this is Mexico, our sister city, and the Sierra Juarez Mountains. But I'd just like to show this sort of as a segue to just, you know, it's an open invitation. If anybody's West Texas like us, there's not a lot of reasons to go to West Texas. But if you're in New Mexico or Arizona, you're close. Yeah, you know, come by Sierra Labs, talk about research, you know. And yeah, if I'm 5 minutes late, so I apologize for that.